Hey guys, so we're going to be talking a little bit about gases today and for the next couple days. And we're going to start by talking about how kinetic molecular theory applies to gases. So remember, kinetic molecular theory is the theory that matter is made of these small particles that are in constant, random, straight line motion. So there's a few kind of assumptions that we make with gases that help us make calculations. So we're going to just title this Kinetic Molecular Theory and Gases. So, first of all, we assume that gases are in constant motion. We already know that from kinetic molecular theory. And they move in a straight line until they collide with something. And they could collide with each other or with their container. We also assume that most of a gas is just empty space. So we assume that the gas molecules themselves actually don't take up basically any volume. So we assume that gas particles have negligible, if you don't know that word, it means something that's so small that it can be ignored. So they don't have any volume that we have to worry about. They're basically empty space. When gas molecules do collide, we assume that they collide perfectly elastically. And I'll talk about what that means. An elastic collision is where you don't lose any energy in the collision. So no energy is lost. They collide and they can keep moving just as fast as they were before. We also assume there's no attraction between the gas particles. Again, there might be a slight negligible amount of attraction, but we just assume there's no attraction between gas molecules. All right, and then their kinetic energy depends on the temperature. So the higher the temperature, the faster they're going to move. So these are some assumptions that we make when dealing with gases. So there's a couple things that we like to measure with gases. The first one is volume. So just want to remind you that the units we use for volume are either liters or milliliters. And that's pretty easy, you know that already. But we also measure pressure. And you may not know the units of pressure that we use. There's lots of different ones. And just let's talk about how pressure happens. Basically, pressure is caused by gas molecules colliding with their container or their surroundings. So these gas molecules are exerting pressure on this container. The more molecules there are, the more pressure there's going to be. Okay, so there is a formula for pressure. It is the force exerted over a certain amount of area, or F over A. So, for example, we can talk about how much pressure the atmosphere exerts. I have that number right here. It exerts 15 pounds per square inch. So that means, like, since you have more than 1 square inch on your body, you are getting 25,000 pounds of pressure pushing down on you. And that's a lot. That's a lot of pressure. So why aren't you, like, collapsing? Why aren't you just getting crushed by this immense pressure? And it's because there's also pressure inside of your body pushing out. So this is like equalized. All right. Now this picture is kind of cool. It shows that as you go up higher, the pressure decreases because there's less molecules. So at sea level, the pressure is going to be greater, than higher up in altitude. Okay, so back in the 1600s, there was a guy named Evangelista Torricelli, and he created this thing called a barometer, which is used to measure pressure. And he created it with mercury, which is a pretty toxic metal. So we don't use that anymore, but it was very useful because it was very dense. So there is a unit of pressure that was developed off of Torricelli's experiment. It's called millimeters of mercury. So there's a bunch of other units of pressure too. So we're going to talk about all of them. The different units of pressure are atmospheres, or ATM, for short, that's the abbreviation. There's also millimeters of mercury, which we abbreviate as mmHg. There's also torr. This is named after that scientist that I just showed you, which is basically the kind of the same unit as mmHg. And then we also use something called kilopascals. Okay, so you need to be able to convert between these different units. So here's what you need to know. 1 atmosphere is equal to 760 millimeters of mercury. 1 atmosphere is also equal to 760 torr, because these are basically the same unit. And then 1 atmosphere is also equal to 101.3 kilopascals. kPa is how we abbreviate kilopascals. All right, so you need to be able to convert between those different units. And we'll practice that in just a second. We want to just talk a little bit now about temperature, because this is another thing we like to measure with gases. We measure volume and pressure and temperature. So temperature is really related to kinetic energy. So let's talk about kinetic energy for a second. Actually, we'll talk about temperature first. Temperature is measured with gases, it has to be in Kelvin, which is K. So in Kelvin, there are no negative temperatures. So 0 Kelvin is the absolute lowest possible temperature where there's no motion. And everything above that is a little bit more kinetic energy. So Kelvin, temperature in Kelvin is proportional to kinetic energy. And you need to be able to convert Kelvin to Celsius and Celsius to Kelvin. So here's how you do that. Kelvin is equal to Celsius, so degrees Celsius, plus 273. So it's really easy. You just add 273 to any temperature in Celsius, and then you'll have it in Kelvin. Now, with kinetic energy, let's talk a little bit more about that. All gases that are at the same temperature will have the same kinetic energy. I'm abbreviating kinetic energy as Ke. Now, having the same kinetic energy doesn't necessarily mean they're moving the same speed. Because remember, kinetic energy is equal to 1/2 mv squared, so there's mass and velocity. So what this means is that heavier gases will move more slowly than lighter ones that have the same kinetic energy. All right, so here's an example. Molecules of H2, O2, and N2 are in the same container at the same temperature. Which one would move with the greatest velocity? So you have to figure out which one is smaller. So if you look at the periodic table, hydrogen's right here, oxygen and nitrogen are right here, so hydrogen's going to be smaller. So hydrogen would move with the greatest velocity. But since they're at the same temperature, they're all going to have the same kinetic energy. So that's yes. Okay, so it's trying to show you that kinetic energy and motion are not exactly the same thing. All right, the other thing you need to do in this section is convert between different units of pressure and temperature. So let's say we want to convert 2.5 atm to millimeters of mercury. We just look at our conversion over here. 1 atm is 760 millimeters of mercury. So our atm would cross out, and I would end up with, if I calculate this, 2.5 times 760, so 1900 mmHg. Okay, now convert 75 Celsius to Kelvin. This is really easy. Kelvin is just Celsius plus 273, so 75 plus 273. Maybe you can do that in your head, but if you want to use a calculator, that's fine. So it's going to be 348 Kelvin. So Kelvin temperatures always look really, really high because they're all just, you have to add 273 to Celsius. All right, so that's a little bit about units used with gases and kinetic molecular theory and how that applies to gases. So let me know if you have any questions.